Welcome to the deep dive. We are about to unpack something that bridges brain science, data, and, well, technology.
Mm-hmm.
We have a description of a specific tool right here, a synthetic EEG signal generator, which sounds like it's a web-based application.
Exactly. And for this deep dive, our mission is, pretty clear. Drawing only from this source material we have, we're going to figure out precisely what this tool is, how it creates these sort of artificial brain signals, who it's built for, and importantly, what its capabilities and limitations are.
Right. So think of this as your fast track to understanding this particular piece of tech. We're going to pull out the most important bits so you don't have to dig through all the details yourself.
Let's do it.
So let's dive in. At its core, what exactly is this synthetic EEG signal generator?
Okay, so the source describes it as a web-based application. It's built using Python, specifically with something called the Flask framework.
Okay.
And its main purpose, its fundamental goal, is to generate artificial or synthetic signals that mimic electroencephalograms, EEG.
Artificial signals. Okay, why? Why would you need synthetic EEG? Why not just use real brain data?
Yeah, that's a good question. The description points right to the key motivation.
Oh,
It's designed for testing and evaluating things like various algorithms, maybe devices, or even theories related to EEG.
oh.
Okay, so if you're, say, developing software to analyze brain signals or maybe hardware that connects to EEG systems, you need reliable data to test against, right?
Sure, makes sense.
And synthetic data gives you a controlled environment for exactly that.
Got it. So it's like a controlled testing ground, maybe a learning tool too.
Yeah.
What kind of features does it actually offer for generating these signals?
Well, it generates signals across the standard EEG frequency bands that most people in the field would know. Delta, theta, alpha, beta, and gamma.
The usual lineup.
Exactly. And the key thing is you can customize the signal you generate. You can adjust parameters for each of those bands, things like amplitude, bandwidth, and also the overall window size for the segment of signal you're looking at.
Window size.
Yeah, the source notes the default is 10.0 seconds.
Okay, so you control the signal strength, the frequency spread within a band, and how long a chunk of data you're analyzing.
Mm-hmm.
And crucially, can you actually see what you're creating, like in real time?
Absolutely. It specifically mentions real-time visualization. It provides both an EEG signal chart showing the wave over time and an EEG spectrum chart.
No, nice.
And because it's web-based, the source says it's pretty straightforward to deploy and access.
That real-time feedback sounds, well, essential for experimenting. Okay, now let's get into the mechanics. How does it actually work? How does it create these synthetic brainwaves under the hood?
So the way it works is by combining sinusoidal waves, basically smooth repeating curves. It does this for each frequency band.
Yep.
And those parameters you set, like amplitude and bandwidth, they control the characteristics of those individual waves.
Right, and the window size you mentioned. What role does that play in the process?
Good question. So once the kind of raw synthetic signal is generated, it needs to be prepared for the frequency analysis part. That's where windowing comes in.
Windowing.
It's sort of like taking specific snapshots or segments of the data. We do this because the standard methods for frequency analysis, like the fast Fourier transform, work best on defined segments. Windowing helps manage weird effects at the edges when you analyze just a piece of a longer signal.
So windowing is kind of a necessary prep step before you can analyze the frequencies.
Pretty much, yeah.
Which brings us to that spectrum chart.
Mm-hmm.
How is that calculated?
That uses the fast Fourier transform, or FFT algorithm. FFT is like a fundamental tool in signal processing. It basically takes a signal from the time domain, how it changes over time, and transforms it into the frequency domain. That shows you which frequencies are present in the signal and how strong they are.
Right, sort of reveals the underlying frequency recipe of the signal.
Exactly. That's a good way to put it. Applying the FFT gives you what's called the power spectrum, and that shows the distribution of the signal's power across those different frequency bands, delta, theta, alpha, and so on.
And that distribution is important in real EEG, isn't it?
Oh, absolutely. Different brain states or activities often show very different power profiles in those specific bands. So seeing that spectrum is key.
It sounds like it's built on pretty standard, solid signal processing techniques. What about the tech stack? We know it's Python.
Yeah, Python with Flask, which is a popular kind of lightweight way to build web apps in Python.
Okay.
But for the, the heavy lifting, generating the waves, doing the windowing, calculating the spectrum, It relies on powerful Python libraries made for scientific computing. Specifically, it mentions NumPy and SciPy.
The workhorses of scientific Python.
Definitely. And it also mentions using the Welch method specifically for calculating the power spectrum. That's a common technique to get a maybe cleaner estimate by averaging the spectra from overlapping segments of the signal.
Okay, Welch method. Got it. And the charts and controls on the web page itself, the user interface.
Right, that's the front end. That uses the standard web stuff, HTML, CSS, and JavaScript. And the library making those interactive real-time charts happen is called Plotly.
Oh, okay. Now, here's something in the description that really caught my eye. It mentions randomness. How does that fit in?
Ah, yeah, this is interesting. This is where it adds a layer to try and mimic real data a bit more.
How so?
So for each frequency band you set up like alpha, say 812 hertz, the tool doesn't just pick one frequency, like exactly 10 hertz, and generate a perfect wave.
Right.
Instead, the description says Python generates a random frequency within that specified range, so somewhere between 8 and 12 hertz in this example.
Oh, okay.
So this random variability means that even if you use the exact same settings twice, the generated signal will actually be slightly different each time.
Huh. That feels pretty significant.
Yeah.
Why simulate that randomness? Why not just make it predictable?
Well, the insight here, I think, is that real brain data isn't perfectly neat and tidy. It's not perfectly consistent.
True.
So simulating some level of randomness within those expected frequency ranges makes the synthetic data, well, a bit more representative of the natural ups and downs you see in actual EEG.
So it makes it more useful for testing algorithms that need to handle real-world messiness.
Exactly. If your algorithm only works on perfectly clean, predictable waves, it's probably not going to do very well when faced with actual brain signals. It's a deliberate choice to make the synthetic data more useful.
That makes a lot of sense. Okay, so given all that, who would actually use a tool like this? Who finds it valuable? What are the main applications the source mentions?
It points to several key areas. First off, research and development. Anything involving EEG-based tech.
Like what?
Well, think brain-computer interfaces, maybe sleep analysis systems, neurofeedback tools.
Yeah.
If you're building that kind of stuff, this generator gives you controllable test data to work with.
Okay, R&D. That's a clear fit. What else?
It's also explicitly mentioned as useful for testing and validating the signal processing algorithms themselves. So developers can use it to create signals with very specific characteristics to see how their analysis software actually performs under those conditions.
Right, like stress testing their code.
Mm-hmm. And it's also highlighted for education and training in EEG signal analysis. Learning these concepts can be pretty abstract, right?
Definitely.
So being able to generate and actually manipulate the signals yourself gives you some valuable hands-on experience.
Yeah, like a simulator for students or maybe researchers just getting into the field.
Exactly that. And finally, it's noted for simulation and modeling of brain activity, perhaps for scientific or medical purposes, where researchers might need to model a specific theoretical signal profile.
Okay, so summing that up, if you're involved in research, development, education, or modeling related to EEG, this tool seems to offer a way to explore concepts, test software, or simulate scenarios without needing immediate access to, potentially complex or expensive real EEG recording setups. It's like a valuable sandbox.
It definitely lowers the barrier to entry for experimentation for sure. But, and this is important, we need to remember it is a simulation. The source is quite clear about its limitations.
Ah, right. Limitations. Good point. What are the key ones? What doesn't this tool capture from real EEG data?
Well, the primary limitation mentioned is that it's a simplified model. It just doesn't capture the full, intricate complexity and all the nuances of actual brain activity. Real brain activity is influenced by countless biological factors interacting in really complex, nonlinear ways.
And what about noise? Noise is usually a huge factor in real EEG recordings. Does it simulate that?
That's a key point the description makes. It notes that while the signals are synthetic, they may not include all the types of noise or artifacts you commonly find in real data.
Like muscle movements or eye blinks.
Exactly. Muscle tension, eye blinks, maybe even the heartbeat signal showing up, or electrical interference from equipment nearby.
Right.
These all contaminate real EEG, but they aren't necessarily part of this generator's output. at least not in its current form as described.
Okay, so the insight there is you probably wouldn't rely only on this tool if you were specifically testing algorithms designed to remove those kinds of noise and artifact.
Precisely. That's a crucial distinction to make.
And what about things like individual differences between people or specific neurological conditions?
Yeah, it uses generalized frequency bands and parameters. It's not really designed to simulate the subtle differences you'd see between individuals, or maybe the specific signal patterns associated with certain neurological conditions, or even specific mental tasks.
Okay.
And it also mentions, kind of circling back, that the power spectrum calculation using FFT is ultimately an estimation. And like any estimation, it can be affected by things like the windowing method used, which we talked about earlier.
Right, so bottom line, it's a powerful and accessible simulation, but you have to be really aware that it's not a perfect one-to-one copy of the, let's say, messy reality of actual brain signals.
Exactly. You need to know what you're working with.
Okay, so given those limitations and strengths, where could a tool like this go next? Does the source mention potential future directions?
It does outline several possibilities. A big one is adding more realistic noise sources.
Addressing that limitation directly.
Yeah, things like white noise, maybe 1F noise, which is common in biological signals, and even electrical line noise, like the 50 or 60 hertz hum. Adding those would make the synthetic data more challenging and more realistic for testing algorithms.
That seems like a really logical next step.
Uh,
What else?
Another interesting idea mentioned is enhancing the spectrum visualization. Right now, it uses a bar chart showing the total power in each band.
Okay.
A potential improvement could be switching to something like a distribution plot or maybe a histogram.
A distribution plot, how would that be different?
Well, the insight there is that a distribution plot could show how the signal power is spread out within each frequency band, not just the total amount.
So instead of one bar for alpha, you'd see a curve showing if the power is concentrated at, say, 9 hertz or 11 hertz within that band.
Precisely. It could reveal more granular details about the signal's characteristics. It gives you a much richer view than just a single bar.
Yeah, that sounds much more informative.
Definitely. Other potential directions mentioned are things like enhancing the user interface with more controls, maybe implementing additional signal processing or analysis features directly within the tool itself,
Mm-hmm.
optimizing its performance and scalability, maybe making it faster or handle more complex signals, and potentially integrating it with other existing EEG tools or software platforms.
So it sounds like a tool with a solid foundation, but also clear pathways for growth, especially towards adding more realism and more analytical power.
Seems that way, based on the description.
The description also briefly touches on some foundational concepts that underlie the tool, doesn't it?
Yes, just briefly. It points to electroencephalography, EEG itself, obviously.
Yeah.
Then the fast Fourier transform, FFT, which we discussed.
They're sort of the theoretical building blocks that the tool brings to life in a practical, hands-on way.
Exactly. It makes those concepts more tangible.
Okay, so let's try to pull this all together.
Hmm.
After digging into this description, what's the main takeaway from our deep dive into the synthetic EEG signal generator?
I think the core insight is that it's described as a remarkably versatile and, importantly, accessible web-based tool. It lets users generate and visualize pretty customizable synthetic EEG signals and see the results in real time, just by tweaking some fairly intuitive parameters.
Yeah.
Its real value seems to lie in providing this controllable environment. It's for testing algorithms, exploring signal analysis concepts if you're learning, or maybe simulating specific brain activity models, all without needing to jump straight into the complexities of real-world data acquisition, at least initially.
And despite those limitations we talked about, it being a simplified model, maybe lacking certain noise types, its utility as a simulation and learning tool seems really clear. It offers this dynamic sandbox for anyone working in or maybe just learning about the field of EEG signal analysis.
Absolutely. It provides a focused way to experiment with the core principles without some of the real-world complications getting in the way immediately.
Which leads us, I think, to a final thought to leave you, the listener, with. Consider that delicate balance, that interplay between simulation and reality, especially when we're dealing with something as complex as biological data like brain activity. How does using a synthetic tool like this help us learn faster, maybe develop technology quicker, and maybe more importantly, what are those vital differences we absolutely must keep in mind when we try to take the insights gained from this kind of controlled simulation and apply them back to the unpredictable, messy, fascinating world of real biological signals?